So welcome everyone to the belated spring school on superstring theory and related topics. My name is Bobby Acharya. I'm a staff member here at the ICTP in the high energy group. I'm here with my colleagues, Pavel Putrov, also from ICTP, and other fellow co-organizer Francesco Benini from CISA, neighboring institute. To start the meeting, I'm going to give a brief introduction to the ICTP. Which has been hosting this school essentially since the 1980s. So the ICTP is the International Center for Theoretical Physics, located here in Trieste, Italy, on the northern end of the Adriatic coast. So the institute was founded in 1964 by Abdus Salam, and part of its aim is to enhance international cooperation through science. In addition to a world-class research program, the ICTP has a mission for developing and fostering science in developing countries. We're governed by three organizations of the Italian government, UNESCO, and the International Atomic Energy Agency. Most of our budget actually comes from Italy, with a significant contribution from the Atomic Energy Agency. And we are administered by UNESCO, and it's through UNESCO that we implement our mission for fostering science. I'll say a few words about the sort of structure of the ICTP. Broadly speaking, we can divide it into three legs: research, education, and outreach. So I'll go through these very briefly in turn. So the research at the ICTP falls into six main groups. So there's our group, which is the high energy cosmology and astroparticle physics group. We cover, broadly speaking, most of the areas in fundamental theoretical physics, also a bit of experimental high energy physics. We have a condensed matter and statistical physics group. So historically, the high energy and condensed matter groups were the first two groups to be formed. We also have a mathematics group, science, technology, and innovation unit, a group which studies Earth systems physics, which could be things like climate modeling or earthquake models, and many other related topics. More recently, we started a group on quantitative life sciences, and we're also expanding in the areas of sustainable energy and high performance computing. There's been some significant contributions from the ICTP over the years. There was the Nobel Prize of Abdus Salam in 1979 for the standard model. We shared in the Nobel Peace Prize Filippo Giorgi, he's the head of our Earth Systems Physics group, was one of the co-chairs of the IPCC that received the Nobel Prize for Climate Change. We have, as I mentioned, an experimental physics group that works on the ATLAS experiment that contributed to the Higgs discovery. One of our high energy physics members, Alexei Smirnov, who's recently retired, has contributed fundamental research to the theory of neutrino oscillations. And our collaborators in our partner institute in Brazil worked on the LIGO experiment, which received a Nobel Prize for gravitational wave detection. So education at ICTP, there's various degrees and diplomas that we coordinate. So we're not a university, so we don't give degree certificates, but we have various programs running jointly with collaborating institutes, most of whom are in Trieste. So that's the University of Trieste, CISA. But we also have a master's degree in complex systems, which involves universities further than Trieste. Our most successful educational program is our postgraduate diploma program, which takes students from developing countries in which there's no comparable diploma program. So at the moment we have a diploma in high energy physics, mathematics, condensed matter, and earth systems physics, so reflecting our research areas. And in each program, we take roughly 10 students in each for 1 year, for the 1 year intense program. And so we've had more than 1,000 graduates since the program started. And as you can see, many of them go on to research careers. We organize, help organize and organize various training activities. So that's something like typically around 60 or so conferences and workshops each year. And that's not just at the ICTP, but we also organize activities in developing countries. We have a significant number of visitors from all over the world every year. And in addition to the sort of main ICTP activities, we also support scientists through additional hosted activities. This is just to give you an idea of where scientists that come to the ICTP come from. And these are statistics that go back around 50 years or so. And we've had visitors from literally 188 countries, making ICTP one of the most international science institutes globally. And we pride ourselves on supporting scientists throughout their entire careers with through the programs that I mentioned, which are starting at the sort of master's level through to PhDs. But then we follow our alumni through their careers. Some of them become what are called associates of the ICTP once they go back to their home countries and join or develop research groups there. And there's a number of other programs that help continue to support our alumni and associates throughout their careers. And once they become faculty members in their home countries, they send students back to us, and so we have a nice cycle of career trajectory. Now come to the outreach part. So the ICTP has had a long tradition of scientific capacity building in developing countries. We have an Office of External Activities that supports and helps coordinate networks, meetings, other types of scientific activities all over the world. In the last decade or so, we've developed partner institutes, most notably in Brazil, China, Mexico, and Rwanda. So, for example, our partner institute in Brazil, the South American Institute for Fundamental Research, was one of the co-hosts of the Strings conference earlier this year, which I'm sure some of you will have attended. Our partner institute in Rwanda has a two-year physics master's program, mostly aimed at students from Africa. And the institute in Rwanda, although albeit smaller and junior at the moment compared to ICTP Trieste, sort of is mirroring the model of, the sort of structure that we have here that I've outlined here. Around 2013, we started the Physics Without Frontiers program to engage undergraduates and master's students, in particular in areas of conflict or rather difficult areas of the world to be studying science. We also have a focus in Physics Without Frontiers on issues like gender in science. And in recent years, we've had projects in Afghanistan, Iraq, Gaza, Syria, just to give you an idea. Then we have the Science Dissemination Unit, which is part of the Science and Innovation Research Department, and they develop all kinds of innovative ways of disseminating science and engaging with the public. And you can read more about more of these things on our website. And this plot is supposed to show you the sort of reach of our scientific outreach just last year. So these are all, every dot represents a different activity and meeting that or outreach event that took place last year. We also do more traditional sort of outreach, and since 2012 we've had the Salam Distinguished Lecture Series featuring physicists giving a series of lectures, typically in January. This is just to highlight some of our former alumni, that so two of whom started off life as diploma students and now have distinguished positions elsewhere in their home. Well, in the case of Narayan, he has a research group in Nepal that we continue to support, and some of you will recognize Freddie over there. So this is just a testimonial from Stephen Hawking some years ago, testifying the impact that the ICTP has had over the years. And there's a similar one from David Gross. And yeah, you can read more details about the ICTP at our website. So now we are ready to sort of open the school. The school is not only supported by funds from the ICTP, but also from the INFN, the Italian sort of National Institute for Nuclear Physics. So we're grateful to them for their support. We have, as you will have seen from the program, 3 lecture courses taking place from Kazuya, Irene, and Alex. I'm now gonna let my co-organizer, one of my co-organizers, Pavel, say a few words about the format and also the Slack channel. Pavel?
Okay, so yeah, first, since we're short on time, so let me just briefly advertise again that we have created a Slack workspace. So you should all in principle have received a link to it, how to join, but I will also a bit later, put the link in the chat in Zoom here. And the idea is that you can ask there whenever you have time, like outside of the dedicated Zoom sessions, you can ask the questions to speakers or to other participants, and people can reply to these questions when they have time, not necessarily immediately. And also, so also you can find some lecture notes there made by our lecturers, which can help you to follow the lectures. And so there are 3 dedicated channels where you can ask questions related to these topics of the courses, and there are also a separate channel where you can ask questions, not necessarily any other questions. And yeah, that's basically it. So Bobby, do you want to tell yourself how the questions during the Zoom will be handled?
Yeah, so I think if you've got questions, just raise your hand on the Zoom. The question sessions are not going to be recorded, so feel free to ask whatever you want. We really encourage discussion and questions as much as possible. Have you got anything else to add, Pavel?
No, yeah, that's it. Yeah, so after each lecture there will be a dedicated kind of discussion session, and it will be not recorded, and neither it will be streamed on YouTube, so you can feel free to ask questions in a formal manner. Yeah, I think that's it. But okay.
So without further ado, then I think we can start. Kazuya, are you able to share your screen?
Okay, so let me share.
So yeah, it's a pleasure to invite Kazuya Yonekura from Tohoku University to give his first lecture on non-perturbative fermion anomalies.
Okay, so thank you very much for the introduction. And first of all, I'd like to thank the organizers for putting together this school in this difficult time. So my lecture is going to be about non-perturbative fermion anomalies. By the way, I'm Kazuya Yonekura from Tohoku University. And so I'm asked to talk about anomalies and symmetries and so on. And I focus on just fermions because they are very basic, and fermions appear in many places in physics. It appears in string theory and high energy physics, and also condensed matter physics. But I should perhaps also mention that there are many other developments in the area of anomalies and symmetries. So there are some generalized symmetries, such as higher form symmetries and non-invertible symmetries and so on. So, so this area is very developing very fast. But I try to be elementary as much as possible. But I needed to assume some background knowledge. So I assume that you know some basics of QFT. And in particular, I assume that you have learned about perturbative anomalies in the standard textbooks. So for example, perturbative anomaly is described by some this kind of triangle diagrams in textbooks. I don't use any technical details of those perturbative anomalies, but at least I assume that you know the concept of anomalies in quantum field theory. And then I will talk about non-perturbative version of anomalies, which is called global anomalies. And also another thing I assume is some basics of geometry and topology. So I use some fiber bundles and their connections. So these are the language to describe gauge fields. And also I assume that you know some differential forms and manifolds. So these are the basic backgrounds. And the reference of my lectures is this paper. This is my paper with Edward Whitten. And so if you want to know more details of my lecture, then please consult this paper. So it contains much more details of my lectures. Okay, so in my lectures, so I talk about anomalies of symmetries, and there are two types of symmetries: so gauge symmetry and global symmetries. So let me comment on these symmetries. So first, gauge symmetries. So I think you have learned, for example, perturbative anomaly cancellation in the standard model. So this is a very basic textbook material. So in the standard model, the anomalies are cancelled very miraculously. So if you have never checked this anomaly cancellation by yourself, then I recommend to do it, this exercise. So this is a beautiful cancellation. And also, anomaly cancellation was one of the important historical developments in the study of string theory. So in type 2B string theory, there is again some miraculous cancellation of anomalies of fermions and also some chiral p-form fields. And in heterotic string theories and type 1 string theories, there is a Green-Schwarz mechanism by which we can cancel perturbative anomalies. So in any consistent theory, anomalies must be cancelled.
Yeah.
Any question? Maybe no? So, okay. So for the gauge symmetry to be consistent, perturbative anomalies must be cancelled. But in principle, we also have to check that there is no anomaly at the non-perturbative level. So these textbooks treat only perturbative anomalies, but at the non-perturbative level, it is more non-trivial to check the anomaly cancellation. And it is even difficult in the standard model. So in the case of standard model, it is possible to show the non-perturbative anomaly cancellation, but it's not so easy. It requires some machinery, mathematical machinery to show the anomaly cancellation in the standard model. And as far as I know, so there is no complete answer in string theory. So no one has demonstrated the non-perturbative, complete non-perturbative anomaly cancellation in string theories. There are some developments in this direction, but still there are many things to be done in string theory. However, maybe you ask this question. So we are very confident that string theory is consistent. So there are lots of studies on string theories, and all these studies show that string theory is really a consistent theory. So we strongly believe that string theories exist. So why do we care anomaly cancellation? So anomaly should be obviously cancelled if the string theory is consistent. And we believe that the string theory is consistent. One of my answers to that question is the following. The study of anomalies in string theory, or maybe also in quantum field theory, is very much related to non-trivial topological structures. And I don't have time to explain the details of this point, but let me mention a few facts. So as an example, let's consider Dirac quantization of fluxes. So string theory contains many p-form fields, such as Ramon-Ramon fields. And so in textbooks, it is argued that they must satisfy some Dirac quantization condition. So Dirac quantization condition of a p-form field is given by this kind of equation. So this equation means that if we integrate a p-form field over some p cycles, then that value must take values in integers up to some constant. So this is the standard statement of the Dirac quantization condition, and it is often assumed. However, in string theory, this is not always the case. And sometimes this condition is modified by additional term. So this integration of the flux does not take values in integers, but it takes values in integers plus some constant, which I denote by A. And it turns out that this contribution is related to anomalies of the world volume theory of D-branes. So Dirac quantization condition, this one, so is usually discussed by requiring the consistency of the coupling of the D-branes to Ramon-Ramon fields, for example. But D-branes contain some world volume degrees of freedom, and they sometimes have some anomalies. Then the Dirac quantization condition is modified in this way. So this means that so if we just naively impose this Dirac quantization condition, the theory is inconsistent. So I believe that the string theory itself is a consistent theory, but it can happen that some compactification of string theories can be inconsistent because of the anomaly. So we have to be careful about the topologies of compactification of string theory, and these topologies are determined by this existence of anomalies. So by this reason, even if we believe that string theory is consistent, we still have to study anomalies of degrees of freedom which appears in string theory. So, for example, yes.
I believe there is a question from Igor. Maybe Igor can unmute himself.
Oh, hello. Thank you. Is correct to say that the anomaly part is computing the cohomology class of the manifold where the field lives?
Anomaly, yeah, in a sense, yes. I don't explain it in my lecture, but it turns out that these anomalies are described by some what is called generalized cohomology. So in that sense, the answer is yes, but it needs a generalized concept of cohomology, not just the ordinary cohomology.
I see. Thank you.
Okay, thank you. Okay, so this is one of the motivations to study anomalies in string theory. And of course, if we consider some theory, some field theory, which is beyond the standard model, then we have to check that the theory has no anomalies. So even if we are just interested in quantum field theory rather than string theory, we still need to understand anomalies as much as possible if we are interested in some new physics. Okay. Next, let me talk about global symmetries. So in this case, the anomalies of global symmetries are called two-hoofed anomalies. So this two-hoofed anomaly is an anomaly of global symmetries. We gauge that symmetry. Okay, so and the existence of anomalies of global symmetries does not imply any inconsistency, but they are very helpful. They are very useful to study the dynamics of quantum field theory. So, for example, let's consider this kind of RG flow, renormalization group flow, from some UV theory to IR theory. Then, so originally Tooft argued that the two-foot anomaly is conserved under the renormalization group flows. So if this UV theory has some global symmetry, and then if that global symmetry has some anomaly, then that anomaly must be conserved in this IR theory. So the anomaly of the UV theory must be the same as the anomaly of the IR theory. So this is a very powerful constraint on strong dynamics, for example. So for example, in the original case of Tooft, this UV theory is the QCD in the massless Tohoku limit. So we consider massless QCD, and then in the IR, the gauge dynamics become strongly coupled, and so because of the strong coupling, it is very difficult to compute what happens in the IR dynamics. So, however, even though we cannot solve the IR dynamics completely, we know that the anomaly must be conserved in this RG flow. Then by using that constraint, Tooft argued in the case of QCD that the chiral symmetry must be spontaneously broken for some color numbers and flavor numbers. So in the massless limit of QCD, there is a SUNF times SNF chiral symmetry. And this symmetry has some anomalies. So they have perturbative anomalies. And by using this chiral symmetry, by using the anomaly of this chiral symmetry, Tohoku argued that these symmetries must be spontaneously broken in the low energy limit if the confinement happens. So in that way, so this Tohoku anomaly is very helpful to study the dynamics of quantum field theory. Okay, and also, I should also mention about condensed matter physics. In the condensed matter physics, the motivation comes from what is called topological phases of matter. So these topological phases of matter includes, for example, integer quantum Hall effect and topological insulators and so on. And in the language of high energy physics, we can understand these topological phases of matter in terms of anomalies in the field theory limit. So in this condensed matter context, Baruch topological phase corresponds to the anomaly of some degrees of freedom which appear on the boundary. So the situation is something like this. So I'm sorry that this figure is not so beautiful. My handwriting is very bad. So here, by this figure, I mean some material in condensed matter. So this material has a bulk, and it also has some boundary. Then if the bulk is some topological phase, then there is some degrees of freedom, some massless degrees of freedom or some topological degrees of freedom on this boundary. And they have anomalies. And the anomalies of this boundary degrees of freedom is completely determined by the property of this bulk topological phase. So that is the basic relation. So for example, in the case of integer Hall effect, in the bulk topological phase, effectively we have some Chern-Simons term in the bulk. And then on the boundary, we have some chiral fermion. And then by the what is called the anomaly inflow mechanism, the anomaly of this chiral fermion is cancelled by the bulk Chern-Simons term. So in this way, so bulk topological phase and anomalies are very much related. And it is believed that there is some one-to-one correspondence. And so this picture is motivated from condensed matter physics, but it turned out that this is also essential for the non-perturbative formulation of the concept of anomaly itself. So this means that even if you are not interested in condensed matter physics, we still need this picture for the understanding, in particular for the non-perturbative understanding of anomalies. And so this picture is very important. For example, if we try to see, so I mentioned that there is some modification of Dirac quantization condition by some anomaly. And this is shown by some, introducing this kind of bulk, and then we can show the shift of the Dirac quantization condition. So this picture is very important. Okay, so this is the condensed matter physics motivation, and also this is important for anomaly itself. Okay, and finally, let me make one remark about this lecture. So in this lecture, I will not distinguish gauge and global symmetries. So I just treat gauge fields as a background field. So in the case of gauge symmetry, we are interested in path integral like this. So we integrate over gauge fields. So this capital A is a gauge field. And we also integrate over fermions. So this psi is a fermion. So we are interested in this kind of path integral in gauge theories. But we can first perform the path integral over fermions. And then let me denote the result by this z psi. So this is the partition function of fermions in this background field A. So in this definition, I only performed the path integral over this fermion. And then for gauge theories, we also perform path integral over the gauge field. But in my lecture, I only consider this quantity, the partition function of fermions in the background field. So gauge field is always treated as a background field. And in the case of global symmetries, so it's very helpful to introduce some background fields corresponding to some global symmetries. So, I mean, so in the case in perturbation theory, we can introduce such a background source field. So, for example, if we have some continuous global symmetries, then there is some corresponding current operators. And we can couple these current operators to some background fields, background source fields. And then we define generating functional. So this contains the information of correlation functions of the current operators. So by taking the functional derivatives of this generating functional, we can obtain correlation functions of current operators. So that is explained in standard textbooks. But we can also consider these background fields which are topologically non-trivial. Then this partition function contains more information, and those information is very helpful in the study of quantum field theory. So even for global symmetries, I introduce some background gauge field. So then I can discuss gauge symmetry and global symmetry simultaneously. So I don't distinguish these two cases. Okay, so any questions so far?
Hello?
Yes.
Hi, just a clarification needed. Whenever you mention about this boundary of this topological, whatever, topological phase, topological object, that picture, this is some kind of real boundary of some kind of material, right?
Yes.
Okay. Okay, thanks. Thanks a lot.
So, yeah. In condensed matter physics, we really have some material, and this is really a boundary of that material.
Okay.
Yes.
Thanks.
There might be another question from Igor. Igor, you can ask, just unmute yourself.
Oh, hello again. We began under the assumption that string theory is a mathematically consistent theory, but we also know that it's a quantum theory of gravity. And there are many evidences that consistent theory of quantum gravity cannot have global symmetries. So how can we identify gate symmetries and global symmetries?
So in the context of string theory, I always consider gauge symmetry. So yes, so there is no global symmetry in string theory. So we believe that. So here I just mean gauge symmetry. For example, type 1 string theory contains gauge group SO32.
Yes.
Then we must check that the anomaly of this gauge symmetry group must be cancelled. And
okay.
Yeah, that was shown by anomaly cancellation in type 1 strings theory, or heterotic string theory is shown by Green-Schwarz at the perturbative level. But as far as I know, no one knows the non-perturbative anomaly cancellation.
Okay, thank you.
Yes. Okay, so if there is no other questions, then let me begin the technical part of my lecture. So first, I want to talk about the relation between topology and anomaly. So I only discuss some elementary examples in this section. And so I assume that you know perturbative anomalies. So I only focus on global anomalies. So global anomaly means some non-perturbative anomaly, even if there is no perturbative anomaly. And then, so we can consider various kinds of symmetries, and we can, in particular, consider, for example, discrete symmetries. So discrete symmetries does not have any perturbative anomalies, but they can have some global anomalies. And in some cases, those anomalies of discrete symmetries are very helpful. And also, we must be careful about the topologies of symmetry groups. So usually in some basic textbooks, so they only care about the algebra of symmetries rather than the Lie groups. But in the study of global anomalies, the global structure of symmetry groups is very important. And I'd like to demonstrate this point by some elementary example. So I consider some topology of symmetry group. And the basic example is the following. So we can consider SU2 symmetry group, and we can also consider SO3 symmetry group and O3 symmetry group. So often in the physics literature, these groups are not carefully distinguished, but for the study of global anomalies, we must distinguish these three groups. So they have different global structures. So their Lie algebras are the same. So their Lie algebras are just described by three generators. So we are very familiar with them in the study of angular momentum. So they have three generators and they satisfy some algebra like this. Ji and Jj. Yes, something like this. So this is a very standard algebra of angular momentum. So because of this reason, because they have the same Lie algebra, they have the same perturbative anomalies. But at the non-perturbative level, we must distinguish them. And first, let me talk about the difference. So first, let me discuss the difference between SU2 and SO3. So there are two related facts about these groups. So first, the allowed representations of these groups are different. So in SU2, we can have spin-out representations. Sorry, no. Some half integer spins are possible. In SU2, but in SO3, we only have integer spin representations. I will make more comments later on this point. But first, let me mention another fact about the difference between SU2 and SO3. So another fact is that some fiber bundles are possible only in the case of SO3 and not in SU2. I will give examples soon. So first, let me explain this first point. So these 2 points are related to each other. And first, let me mention this point. So for example, we can take U1 subgroup of SO3. So let's say that this is just a rotation around the z-axis. So this U1 inside SO3 may be realized by this kind of group elements. So we take this generator J3, and then we take the exponential of this J3. Then this represents the rotation around the z-axis by the angle phi. So we can take this U1 subgroup. Then the exponential of 2 pi ij3 is, so this is identically equal to 1 in SO3. So this means that 2 pi rotation is just the identity. So this is just the usual fact in 3 dimensions. So, but this means that so this means that this J3 cannot take values in half integers. It cannot be some 1/2 plus integers. So in SO3, half integer representations are excluded, and only integer representations are possible in SO3. So this is the basic difference between SO3 and SU2. And next, let me consider some fiber bundle. In the case of SO3, we can consider the following non-trivial fiber bundle on S2. On S2, I take some polar coordinate, theta and phi, just the standard polar coordinates. And then I take the gauge field A, the gauge field of SO3 to be like this one. So maybe I should write a figure. So this is S2. So S2 has some north pole and south pole, and there is some equator. And then on the northern hemisphere, I take the gauge field, which is given by this formula. So I take the gauge field like this in the region theta is less than 2 pi. And in the southern hemisphere, I take the gauge field to be like this. Okay, so if you are familiar with some Dirac monopole configuration, then I'm just taking Dirac monopole configuration by taking the, so I take the U1 subgroup inside this SO3. So this J3 is the generator of the U1 subgroup. And then in this U1 subgroup, this configuration is just a configuration of Dirac monopole. And this configuration is consistent because we can glue the gauge field in the northern hemisphere and southern hemisphere in the following way. The gauge field in the southern hemisphere is given by gauge transformation of the gauge field in the northern hemisphere. So these two gauge fields are related in this way. And here, the gauge transformation parameter, this G, is given by exponential of ij3 phi. Okay. So we can glue these two gauge fields by this transition function. So by this transition function, and so this is consistent for SO3. Well, in other words, this function G, this gauge transformation function G, is single valued for SO3 group. So in the case of SO3, this function is single valued, so this gauge transformation is consistent. But in the case of SU2, this is not consistent. In the case of SU2, this J3 can take half integer values. Then this function G is not single valued. So this configuration is not possible in the case of SU2. So this is only possible in SO3. So in this way, so which representations are possible and which fiber bundles are possible are closely related to each other. So for the purpose of my talk, SO3 has more interesting topology. In fact, we can see this function G as a map from S1. So this S1 is the equator here. So we have S1 here. So this G is a function from S1 to SO3. And the topological characterization of this function is given by the homotopy group, the first homotopy group. So this G gives so topologically, this map is classified by the fundamental group. So the first homotopy group, pi1 of SO3. So this pi1 of SO3 is known to be Z2. And this so this example is known to be a non-trivial element of this Z2. So this has a this transition function has a non-trivial topology, and that is the reason that this bundle constructed here is topologically non-trivial. I don't explain the details here, but yeah, anyway, so this is a kind of well-known fact in mathematics.
Sorry, Katsuya, there is a question in chat.
Yes.
It asks, isn't G a map from S1 to the group U1?
Yes. So yes, that's right. So this map factors like this. So this is a map from S1 to U1. So this U1 is a U1 subgroup inside SO3. And then this, so because this U1 is a subgroup of SO3, we can further map this to SO3. And because we are interested in this SO3, I just wrote directly the map from this S1 to SO3. Okay, but maybe I should mention that, yeah, so in the case of U1, this homotopy group of U1 is given by the set of integers. So this means that the non-trivial bundles on this S2, non-trivial bundles on S2 are classified by integers. And these integers are precisely the magnetic flux of Dirac monopole configuration. So this integer specifies the magnetic flux. And so this fact about SO3 means that we can have a kind of magnetic flux for this SO3 gauge group. But this magnetic flux is conserved. It is topologically stable only mod Z2. So if we combine two magnetic fluxes of SO3, then the combined flux is trivial. So that is the meaning of this homotopy group.
Kazuya.
Yes.
We should think about entering the discussion session soon.
Okay. Yes, okay. Maybe I stop here and then let's go to the discussion session.
Thank you very much for this very nice opening lecture. So we're going to stop the recording here and enter the discussion session, but let's thank Kazuya before we do that. Harvard and Madrid, it seems. So yeah, please take it away, Irina.
Okay, thank you, Bobby, and thank you for the invitations to give these lectures here, and thank you to all the students for coming here to listen. So yeah, my name is Irene Valenzuela, and I'm going to tell you about the Swampland during this week. So I'm not expecting you to know about it. I mean, I will try to be as pedagogical as possible and start from the beginning. So please, the most important thing is that if you have any question at any time, don't hesitate to interrupt me, okay? You can just stop, ask any question. I mean, don't worry if it looks very stupid or very clever. That's not the point. We are here to learn, okay? So let's start. Okay, so these are here some references that I put out the Swampland. As I said, my goal is try to be as slow as possible. So of course, we will not be able to cover everything that has been done. So if you want to know more, these are nice references. I will mainly follow this reference here, which comes from another course that I gave last year. So also the things that I'm talking here, I mean, if you don't understand something and you want to know more details, you can just check this paper and you will see everything explained in a bit more detail, but with the same ideas and same philosophy. Okay. And also, yeah, as I said, if you want to know more or especially know the references, you can check this review of Rampalti or another TESI lectures from Kuru. Okay. So let's start. Let's try to define what is the Swampland. Okay. So the idea of the Swampland, okay, we'll see that we are going to break with this intuition of effective field theories. Okay, so let me start putting us all in the same page and defining what are typically effective field theories. Okay, so effective field theory is something that we use all the time in physics, has been very useful to progress in high energy physics because we can provide a description of the theory that is valid up to some energy scale, which we call the cutoff, and describes the physics around that scale without worrying too much about what happens in the UV at higher energies. Now, if we have some UV theory, okay, some theory that is valid in the UV, we can always integrate out the degrees of freedom up to some high energy scale, up to some cutoff, and obtain some infrared description, okay? So this is integrating out. And here we get, as you have probably learned many times, you get some renormalizable part plus an infinite tower of non-renormalizable operators that are valid up to the cutoff of the theory, which I call lambda. Okay. Okay. This is very nice. The problem or the thing is that it's not guaranteed whether the reverse process can always be done. Okay, so that given some effective field theory that you construct from a bottom-up perspective, following the rules of quantum field theory, like for example, you require that is unitary or anomaly free and so on, is not guaranteed that this will have a UV completion. Okay, so that you can go back. Okay. So this is something that already happens in QFT, but in the presence of gravity is even less clear, okay, whether any EFT can be UV completed in quantum gravity. And the fact that this is not always possible is what is underlying the Swampland program that we will discuss. Okay, so not every EFT can be UV completed in a quantum gravity theory. Okay, so it's not compatible with a quantum gravity description at higher energies. And the goal of the Swampland is try to understand what are the constraints that effective field theory must satisfy to allow for this UV completion. Okay. So of course there are some things that we know, like anomalies, right? You need to satisfy gravitational anomalies now to be able to complete it in quantum gravity. But the point, what we are learning from string theory and also thinking of black holes, is that this is not enough. Like you need to require more things to guarantee that you reach some unitary quantum gravity description. Okay, any question about this? Okay, so this is the typical picture that we put about the Swampland, in the sense that if you imagine here, like in the horizontal axis, all effective field theories that you could construct following the rules of quantum field theory, not all of them will have a UV completion, as we are saying, only a subset, which we call the landscape. So this is consistent with quantum gravity. Can be UV completed, and this is not consistent. And the theories that are not consistent, in the sense that they don't satisfy these additional constraints, we say that they belong to the Swampland. Okay, And the name was chosen precisely in opposition to the landscape, which are the theories that, the effective field theories that can arise as low energy descriptions from string theory, for example. So one of the most important things of how to distinguish a Swampland constraint is that it should disappear if the Planck mass goes to infinity, right? Because it's a gravitational theme. So if you decouple gravity, the constraint should completely disappear. And that's why, like in this cone, if the UV completion is infinitely far away, like everything is allowed. Okay, and the constraints become stronger and stronger as you increase the energies typically. Okay, so for example, you have some effective field theory that lives here. Let's pick another color. Yeah, it's here in the landscape. Maybe at this energy scale is fine, it's an effective field theory that makes sense, but if you want this effective field theory to be valid up to a higher energy scale, there is a moment in which it's going to find like this boundary of the cone. This is a bit qualitative, but like to get you an intuition. I mean, at some point we'll probably hit this boundary, which means that the effective field theory will not be valid anymore unless you modify it. And sometimes these Swampland constraints are telling you what is the scale at which this happens. Okay, so what is the cutoff at which you have to modify that effective field theory so that it's still within the cone that is compatible with quantum gravity. So that the cutoff in which new physics has to appear and you have to modify the theory seems to be below the Planck mass. Okay, so this is one of the lessons that we will learn from the Swampland program, that this cutoff, this quantum gravity cutoff, which quantum gravity is telling you that you have to modify the theory, is below the Planck mass, which is the naive cutoff that we put for quantum gravity. Okay. As I said, if there is any question, just interrupt whatever comes to your mind. Okay, so if this is true and if there are these new constraints that we need to satisfy, I think it's amazing news, especially for phenomenology, because basically we are giving new constraints that effective field theory can satisfy, so they can be used as new guiding tools to progress in high energy physics, and they are capturing the quantum gravity imprint at low energies. Okay, so we are saying that quantum gravity can matter at low energies, even if the Planck scale naively is very high and seems that gravity is very weak and quantum gravitational effects are not important. Still, to guarantee a quantum gravity consistency at higher energies, there are non-trivial constraints, and this can also solve, like, bring new insights into the naturalness issues that we observe, because they are kind of breaking this expectation of separation of scales between the UV physics and the infrared. Okay. So you might wonder, like, how is this possible that these constraints are important, in the infrared? Like, we always learn that when you integrate out all the heavy fields, in the end, maybe you generalize some non-renormalizable operators, but this is going to be suppressed. So the effects should not be so important. So why is it so important to consider all these corrections? Well, the point is that in the presence of gravity, this intuition can fail. Okay, so we can really have a mixing between the UV and the IR physics. So this Wilsonian effective field theory approach can fail. And an intuitive way to see this, I mean, very intuitive, is thinking of black hole physics. So if you imagine, okay, if we have some black holes, okay, so let's think of black holes. If we imagine that we scatter particles at very high energies, right, like what we do at the LHC, higher energies, right, typically imply smaller distances, right? So by scattering at higher and higher energies, we prove smaller distances. However, there is a moment in which if we continue going to higher energies, we are going to start generating a black hole, right? And a black hole will be larger and larger, okay? So that putting more energy into the system does not give rise to proving smaller distances, but now proving larger distances, okay? So we break this notion that higher energies go to smaller distances and so on. Okay, so this is very intuitive hand-waving argument. But mainly the point is that by studying string theory compactifications and also black hole evaporation in more detail, you can derive these new Swampland constraints, okay, that we will study in these lectures. And what is more interesting is when these constraints go against the effective field theory expectations, okay, when constructing beyond the standard models and so on. So the examples that we will see is that some features which are completely fine from the perspective of quantum field theory, like global symmetries or small gauge couplings, right? So we have a perturbative description of a gauge theory. Or for example, large field ranges. Okay, so we can have models of large field inflation and so on. These things are problematic in quantum gravity. Okay, sometimes we'll see that this implies that they cannot happen and we'll have to break the global symmetries. Sometimes it means that if you want to engineer small gauge coupling or a large field range, the cutoff, the quantum gravity cutoff is going to be very low. Okay, it's going to go to 0. So new physics have to appear soon. Okay. Okay. Any question? I'm going to continue asking for questions unless someone is brave enough to ask.
Sorry, Irene, there is a question in chat.
Ah, okay. Sorry, I didn't see it.
Should I read it for you, or you can read it?
I can read it. So the question is, if suitable modifications bring an EFT back in consistent region, can I sharply distinguish landscape from Swampland? Yeah, the thing is that the notion of landscape of Swampland is depends on the energy scale. That's the point. Okay, so some of the constraints, I mean, depends which one. Okay, some of the constraints, since the Planck scale is finitely far away, some of the effective field theories will always be ruled out in the deep IR. So there are some effective field theories which cannot be there, and some Swampland constraints are sharp in that sense. Like for example, you cannot have global symmetries, but others are related to this cutoff. So that they tell you, okay, if you want to engineer this feature in the EFT, the cutoff has to be at this energy scale, which means that if you are above that energy scale, that theory is inconsistent. But if you are below, it's still consistent for some energy range. So this distinction sometimes will depend on the energy scale at which you want the effective field theory to be valid. Okay.
I also had a question. Well, maybe just ask to maybe clarify a bit more. What did you mean with the small gauge couplings are a problem? Or maybe you will come back to it later in the lectures. But... Yeah.
So these are the main three consequences of the main three conjectures that we will see. The small gauge coupling is because we'll be constrained, for example, by the weak gravity conjecture. That we'll see also that if the gauge couplings become very small, which in principle should be fine in quantum field theory, right? From the quantum gravity perspective, that's too close to restoring a global symmetry. Like if the coupling is going to 0, it's becoming very, very small. Yes, you have a very approximate global symmetry. And that's problematic and will mean that the cutoff of the theory has to go linearly with the gauge coupling. So if the gauge coupling is very small, the cutoff also becomes very small. We'll see that.
Does that mean if I just have let's say some classical gravitational background and I want to put some gauge theory on top of it,
yes.
I get in trouble? So there's essentially no perturbative gauge theory on top of some...
I mean, as I said, it's going to be a relation of the cutoff. So there is always some perturbative gauge theory below a certain cutoff, but this cutoff is something that you cannot extract from quantum field theory, right? It's a quantum gravitational effect that is telling you that the cutoff is also going to 0. So it depends what energy scale you want to describe this effective field theory, then will be a problem or not. So there's a correlation between the cutoff and the gauge coupling. And yes, let me remark, that's a good point. All I'm talking about here will be about effective field theories that are weakly coupled to Einstein gravity. Okay, so we take an effective field theory in quantum field theory, and we couple the theory to a semi-classical gravity description, Einstein gravity description, and then we wonder whether that effective field theory will continue to be valid at quantum level, right? When we consider quantum gravitational effects and what are the constraints. Any other question? Okay, simple question. Good, very good, people. So it's right to say that the theories following Swampland need not be made consistent with quantum gravity. So if you say a theory is in the Swampland, is because, I mean, when you say when you give an effective field theory, an effective field theory is also it also comes together with the definition of the cutoff, like what is the energy scale at which that effective field theory is valid. So if you are saying that effective field theory at that energy scale is in the Swampland, then it's not consistent with quantum gravity. It's kind of part of the definition of the EFT. Okay, any other question? Okay, good. So this was the introduction. So let me, okay, so this is a map.
I have a question too.
Yes, sure.
Sorry, what is a large field range? What do you mean by large field range?
Yeah, so we will see this in more detail, but
okay.
I mean, if you have some scalar field, right?
Mm-hmm.
The scalar field can take different vacuum expectation values.
Mm-hmm.
In principle, that value is not constrained, could be whatever, right? From a quantum field theory perspective. It could even be very large. It could even take a Planckian expectation value, as long as there is no energy that apparently comes above the cutoff, right? Like, I mean, the field, I mean, the scalar fields can take Planckian values as long as the energy doesn't go along the cutoff, and that's in principle completely fine, and that's what we use, for example, to construct large field inflationary models. But from the quantum gravity perspective, we'll see that there is also a sort of cutoff in field space, like how large these vacuum expectation values can be.
Okay, see, thanks.
Okay, so this is a map of the most important Swampland conjectures. What I'm going to do, so let me put a bit of order here, and then I will tell you what we will do in detail is to study the ones that are in black, okay? So the absence of global symmetries, the weak gravity, and the distance conjecture, because they are really at the core of the Swampland program. I mean, these are the most important ones, and many of the others can be derived from relations to these ones, and also are the ones that have been more studied and are better understood, and they are in solid ground. Okay, so it's very important to have these three conjectures very clear, because from then we can start constructing other things. Okay, and we can start giving also more constraints on the potential and so on. But that only makes sense if these three conjectures are like very, very clear. Okay, so just to put a bit of order, the first row here, everything can be related, and actually this year we are unifying these conjectures into a single statement. Okay, so everything is about constraining what is the notion of global symmetry that is not allowed in quantum gravity. Okay, so this is about constraining the kinematics, and basically it's really everything is correlated to the absence of global symmetries that we'll study in detail. Now the next row is they are giving constraints on the field spectra. Okay, so these ones are the ones that tell you that if you want to engineer small gauge couplings or large field ranges, the cutoff is going to go to 0, and you will have new physics. Okay, so we'll see this in detail. Basically, we will get towers of states that are becoming light, such that this quantum gravity cutoff becomes below 1 Planck. Okay, and then
I'm sorry,
yes.
can I? Because
yes,
you
sure.
insisted to questions.
Yes, all the questions are welcome.
For the first line, the no global symmetry, so it's a conjecture, right? But then, if there, I guess a conjecture has some meat to it. But is there a direct distinction in this conjecture for discrete and continuous symmetries, or I mean?
So we'll see that the conjecture is in general both for continuous and discrete. Although there are different works given evidence for this, and depending what work then applies to both continuous and discrete, or only to continuous, and so on. So okay. Yeah, I will tell you later the evidence, then you can tell me like exactly if you want to know like
okay.
Yeah, where these symmetries are. Yeah. Okay, and the last part are the newer conjectures, okay, that have appeared recently and that are still on progress, let's say. So it's like here from the weak gravity and the distance conjecture, if we apply to scalar potentials, actually these are like constraints on the potentials. In certain setups, we can see that they imply stronger constraints, which tells you some features of the scalar potential or the vacua that are consistent with quantum gravity. And these are conjectures that can have much stronger phenomenological implications, but are also still in the process of understanding what is the exact statement that is realized. Okay, so this is evolving very quickly. And that's why when you hear about the Swampland, it's important also to keep in mind what Swampland statement you are talking about. Okay, it's not the same if you are talking about no global symmetries that we already have a lot of evidence and also proofs in certain setups, you see, like AdS EFT or perturbative string theory and so on, that if you talk about the sitter or other things, because it's still in progress, I mean, we have to, I mean, there is something there, but it's not completely clear what is the sharp statement that is realized. Okay? And part of most of the research is precisely trying to define properly what is the precise constraint that should come from quantum gravity. Okay. So, okay, so let's focus then on the black ones. The last day, depending how we go on time, we'll talk a bit about the last ones on the bottom. Okay, I can tell you what they are about and what we know, what we really know about them, and what is the evidence that we have, and what is missing, like what are the open questions. And if there is someone in particular that you are more interested in, you can also tell me by Slack or something. Okay, like, I have heard about this statement. Can you talk a bit about it? And we'll discuss it the last day. Okay, so as I said, the plan of the lectures after this very long introduction is to talk about no global symmetries, which is the most important one. So we'll be talking the rest of the day about this and also part of tomorrow. And then we will discuss the presence of all these towers of states, like these new states that appear when we try to engineer like weak gauge theories and large field ranges and so on, and how this gives rise to this weak gravity and distance conjecture, okay, from the string theory perspective. And then we will see how this particular weak gravity conjecture can be also independently derived from black hole physics. Okay. And as I said, at the very end, we'll see how much time we have to discuss the constraints on the scalar potentials and the string landscape of vacua. Okay. So any question before I start with no global symmetries? Okay, very good. So the absence of global symmetries is the most, I think, is one of the most important Swampland statements. It's actually very old. And I mean, we'll see, for example, you can already find an explanation of it in the book of Kolczynski about string theory. But in order to discuss it, I want to explain carefully what do we mean with global symmetry, okay? How to distinguish a global symmetry from a gauge symmetry and so on. Because this doesn't mean that there are no symmetries whatsoever in quantum gravity. Okay? It's just that the symmetries, if we have an exact symmetry, it has to be gauge, in the sense that it has to be associated to some gauge degree of freedom. Okay? It's like the global part of the gauge group. So the intuition to distinguish between global versus gauge is that global charges, as I put here, cannot be measured from very far away. Okay, so this is kind of a hand-wavy intuition, but it's precisely what is behind all these black hole arguments. I mean, why we cannot have global symmetries. Okay, it's kind of the idea that everything, it's kind of a holographic perspective of the world also, that everything can be measured from very far away. So to give I think it's easier sometimes to give examples. So let's give some example and then we'll give a more proper formal definition of this. So the typical example is, for example, if you just have some axiom, like some scalar field. Okay, this is invariant, right, under a shift symmetry. Okay, so I can transform phi with phi plus lambda. And this has some global charge, which by nether, since I have a Lagrangian description, this is just the integral of a current, which in this case you can compute by using nether theorem, that is star d phi. Okay? So that this current is conserved. Okay, now this is an example of a global symmetry. Okay, that should not be allowed in quantum gravity because this is conserved. Now there are two options. You can either break it, okay, so we can add a scalar potential, for example, so we break the shift symmetry, or you can gauge it. Okay, so the usual procedure, as you have learned many times, is that we can gauge it by coupling to a gauge field, right? To a gauge field A, so that we add an extra coupling of the current to this gauge field. And let me put a kinetic term for the gauge field as well. Okay, so this is the typical Stuckelberg coupling. Okay, and we can just, I mean, this is the, write it this way, if you wish, that the gauge field is eating up, right, the scalar, and the global symmetry now is gauge, because this Lagrangian is only invariant under the combined transformation of the axion and the gauge field, right? So when phi goes to phi plus lambda, I mean, we can, now this lambda can be local, actually, can be a local parameter. So A1 goes to A1 minus d lambda. And this is a gauge transformation, right? So if lambda x at infinity goes to 0, this is what we call gauge, right? Local gauge transformations. And these are redundancies of the theory. But those transformations that are global, no, that go to a constant at infinity, are global transformations, and they really act on the Hilbert space of physical states. Okay, so this is a symmetry of the theory. This is a global symmetry, but it's a global symmetry which is fine in quantum gravity. So we don't call this global, but we call it gauged. Okay. Or sometimes people call it like the global part of the gauge group. Okay, so this is fine for quantum gravity. Okay, while the previous one without the gauge field should not be allowed. Okay, this is the, I mean, just in a very simple example, what is the distinction?
Sorry, Irene, I have a question.
Yes.
So when you say that the symmetry must be either broken or gauged, by broken you mean explicitly broken, or would
Yes.
spontaneously broken be okay?
No, I mean explicit breaking. I mean, in the end, spontaneous breaking is like you still have a symmetry, right? It's just that this, in particular, the vacuum, but some state that breaks the symmetry, but it's still an exact symmetry in your theory and your description. So that's not allowed. No, it's not enough with the spontaneous breaking.
Okay, thank you. Okay.
So this is like the, okay, so this global part is like the electric charge, no? Like the electric charge that we always talk about. If you write the current, I mean, the equation of motion for the gauge field, right? Now this is going to get modified. Okay, so that you get this electric charge. And this is something that we can measure from very far away. Okay, that's why there's this intuition or distinguish between global and gauged. Okay. So I'm going to generalize this and give you a more formal definition of global symmetry. But before,
sorry,
I want to
ask
give you
another question.
Yes, sure.
So, so I would like to understand better what is the intrinsic distinction between, say, standard global symmetry and the example that you gave here of global symmetry that comes from boundary conditions. Is it related to superselection sectors? Or?
So that is for me the easiest way. So we'll see, but I think the most precise way to distinguish them is when you then write it in terms of what are the charge operators that are the operators that are charged under the symmetry. I mean, whether they are gauge invariant or not. So whether, I mean, we'll see that, I mean, now we will formulate this all in terms of topological operators and charge operators. And the difference between this gauged global symmetry and the previous one is that the operators that are charged under the symmetry are gauge or not gauge invariant. So whether you have genuine operators that are charged. And this is very sharp because you can just, right, like classify all the operators that you have and check if you have any operator that is genuine, so it's gauge invariant and is charged under some topological operator. And that will be the...
I see. So we can say that so this symmetry is okay because there are no gauge invariant operators which are charged under this symmetry.
Exactly.
Okay.
That will be, we'll see in a couple of slides, but yeah, that's the sharpest thing. Okay, so before going to this sharper definition, I thought it can be useful to give you, I see there are more questions. Yes. Why charges of global symmetries can't be measured far away? Well, intuition is because, I mean, how you measure, right, some symmetry, because you have some dynamical degree of freedom. Like for example, when it's gauge, it becomes the electric charge. So you can measure it because you have the gauge field, right? And you can make an experiment to measure the gauge charge from very far away, because then you have a Gauss law, right? So a Gauss law is something that appears only when the symmetry is gauged. And even if it's discrete, and you would say, okay, but then I don't have like a dynamical gauge degree of freedom, what's going on? Still, you can have like an Aharonov effect, and you can measure from far away. So you need to have some dynamical, like some degree of freedom associated to it. And if it's global, it's completely global, like we didn't have the gauge field, there is no experiment that you can think of that you can measure that charge from far away. There is no Gauss law, there is nothing like that. Okay. This is kind of the intuition. And we'll see also that it becomes, I mean, right now we'll see that it becomes very clear also when thinking of black holes, because the black holes, the horizon depends on what is the gauge charge, but that's not, I mean, this electric charge, but is blind completely to global charges. So from very far away, you cannot see if the black hole is charged under a global symmetry or not. We'll see. Okay, let me go on slide. We'll see why it's important that can be measured from far away. Okay, so let me, exactly. So before getting to more formal definitions, I want to give you an intuition of what is the problem with that. Okay, now I just gave you a distinction. Okay, so this is the difference between two types of symmetries that we can have. The intuition is that one can be measured from far away, the other one cannot. But why is that? Why is that a problem? Okay, so why these global symmetries should not be allowed in quantum gravity? Okay, so here I put like what is the evidence that we have for this conjecture. There are some proofs that we have, okay, in string perturbative theory that you can already find in Polchinski book, because any global symmetry of the worldsheet gives rise to a gauged symmetry in space-time, okay, and you cannot have global symmetries in space-time because, I mean, global symmetry is something that are conserved, like it doesn't matter of the duality frame. So all the global symmetries in the worldsheet are gauged in the space-time. So you can only have gauge symmetries in space-time. And the same happens in AdS-CFT, thinking of the like global symmetries in the CFT are gauged in AdS. The thing is that this proof in perturbative theory works for continuous symmetries when you have a current. Okay. But recently, by Harrow and Oguri, they generalized this to talk about more general symmetries, even if they are discrete, as long as they are splittable in the boundary. So to explain all these things, I don't know, you need to know many more things also about entanglement, wedge reconstruction, and so on. So I think I will not explain it here. But if you want to know more about these derivations, after the lecture, I don't know, like half an hour later or whatever, like you can stay and you can ask me about it and I can tell you in more detail what the proofs are about, okay? Instead, what I want to do now is to give you what are the black hole heuristic arguments, okay, of why these global symmetries are not allowed. So you have at least some intuition of what goes wrong if you cannot measure the global charge from far away. And also let me remark that recently there are also many more works trying to make more concrete this absence of global symmetries from black hole physics, because all the recent developments regarding the unitary, like the derivation of the page curve, right, for the unitary black hole evaporation, are also useful to show the absence of global symmetries. And people have shown that all these wormholes that are breaking the global symmetries, or more generally, whenever you have some topology changing process in quantum gravity, this is going to break global symmetries. So we'll see that having a global symmetry is in one-to-one correspondence with having some topological operator, okay, something that is invariant under diffeomorphism because it has to commute with the stress energy tensor. And that's fine in quantum field theory, because in quantum field theory we fix the topologies. But in quantum gravity, topology is something that can fluctuate, can change. And this gives you an intuition why global symmetries are not allowed, because then we cannot have topological operators. Okay, so let's do this. So let's study these heuristic arguments, okay? And then we will define sharply what are exactly, how to identify the symmetries that are not allowed, and how all the recent progress in quantum field theory generalizing the notion of symmetry also can have very profound impacts here. Okay, so just the heuristic argument. So why is it a problem if I cannot measure from far away? Well, if you think of a black hole, this is the metric, for example, for a Schwarzschild black hole that is neutral. So by the Noether theorem and so on, I mean, we know that the metric, the horizon, right? The horizon is not sensitive to the global charge. Imagine that we have different black holes that are charged under a global symmetry, so we can construct a black hole for all possible charges. Global charges. Okay. All these black holes, even if they have a different global charge, they have the same metric. Okay. So from far away, they look the same. And now this, the fact that you have infinitely many ways, like you have infinitely many possible charges, for example, under some U1. So infinitely many ways to describe the same horizon, the same object from far away, gets translated to some like infinite uncertainty that naively it should give rise to some infinite entropy associated to the black hole, right? Like if we think that the entropy of the black hole is associated to how many different ways, no, like how many microstates we have. If we have some black hole charged under a global symmetry, this would give rise to infinite entropy and would be against the expectation of Bekenstein bound, that we have always a finite entropy for the black holes. Now you can make this a bit, I don't know if more precise, but more quantitative if you think of like constructing black holes for every possible value of the charge and letting the black holes evaporate. Okay, since Hawking evaporation is blind to this global charge, in the end, you are going to end up with like an infinite number of very long-lived, almost stable remnants of size and Planck. Okay, this is the size. And this is what is called the trouble with remnants, in the sense that we can count how many of these black holes we have, which is going to be a sum of e to the s. No? This is the number of states where s is the entropy. And now we have to sum over all possible charges, global charges, and the masses, and this goes to infinity. So having an infinite number of states in a weakly coupled description of Einstein gravity doesn't make sense because everything couples to gravity, and this is going to renormalize the Planck mass, and it's not going to be Einstein gravity anymore. So this is the idea that exactly this effective field theory weakly coupled to Einstein gravity doesn't make sense. Okay, and we'll see when talking about the weak gravity conjecture how this trouble with remnants is solved if you have a gauge charge instead. Because if the symmetry is gauged, then this metric now will have a Kerr black hole, and the metric is sensitive to the value of the charge. So we'll have different different black holes for each possible value of the charge. And when counting the number of remnants, will be finite. Okay. Any question about this? This is a heuristic argument.
Hello, can I ask a
Yes.
question? So what you're saying here, if I understand correctly, is that so you calculate any process in an EFT coupled to gravity, and because you have an infinite amount of states, you have sort of an infinite amount of states and loops that you need to sum, and you get infinity for anything that you try to calculate. But is there a possible caveat that there could be a form factor for these black hole states and the loops because it's an extended object, or some kind of form factor that allows you to regularize that sum? Has this been?
Yeah, so form factors are actually very important. I mean, when you can wonder also why a black hole, already a single black hole, no, it's not spoiling the loop computations that we do in the standard model, and that's because of these form factors, right? And also because if you try to compute it, you will see that you get a suppression in terms of the entropy, like e to the minus s. So that's important for that. Now, if we have an infinitely many, then at least the naive computation, if you try to do it actually, is that this e to the minus s will precisely cancel by the number of remnants, like you have infinitely many, so that they should not be suppressed. Now, this is like I don't know if to say naive, like, I don't know, if you do it the vanilla way, I don't know if there is any way to complicate things such that you have some form factor that could suppress it. And I think, I mean, nobody has proposed anyway, like there is no quantitative way to do that. But I mean, I for these type of reasons, I like to emphasize this is just like a heuristic argument. I mean, it's not a proof, because there can always be caveats if we don't know what is the quantum gravity completion, right? Like, how do we do this computation? I don't know, maybe we are missing, what are these form factors somehow. And with quantum gravity, we'll change it in a way. But you always have to take these arguments as a motivation of that this is telling you, okay, here there is something funny. Like if you try to do it, since you have infinite many states, it's true that there is a sharp, like gravity seems to distinguish whether it's a global or a gauge symmetry. Black holes are not sensitive to that, are blind, so it seems that this gives rise to an infinite entropy. So this is something here that is weird. Let's now study this more quantitatively, string theory or AdS EFT, and see if we have a proof for that. Okay, that's the way you should take it. So yeah, I mean, could be caveats. Okay. Okay, see, there's another question. Can you say something about SL2C in type 2B? Say how, why is it gauged? Yeah, so all the duality symmetries that we have in string theory are gauged. Okay, like dualities in general, right? They are like kind of gauge transformations. And sometimes we can even understand how they arise from a DFO or a gauge invariance in higher dimensions. So for example, the SL2C, you can see that this gauge, you can see it in the worksheet, like you can describe SL2C in type 2B perturbative string theory and see that it corresponds to something global in the worksheet that becomes gauge in space-time, and something that you can do sharply in the worksheet, but also in space-time, like without having a worksheet description from F theory perspective. I mean, since it becomes part of the diffeos of the torus, diffeomorphism of the torus of the elliptic vibration, you can kind of see, that it's gonna be a gauged symmetry because it's associated to gravity, to the geometry. Okay. Okay, so let's now define this more precisely. So the point is, okay, so this is the situation that we had a few years back, okay? Now, in parallel, in quantum field theory, there's like a mini revolution regarding generalizing the notion of symmetry, okay? So there are many more symmetries in addition to this axionic symmetry that I told you about. We have P4 global symmetries, non-invertible symmetries, many things. And this also has an effect here because all these global symmetries, they are, I mean, these new notions of symmetries are still global symmetries. So they should still be absent in quantum gravity. And we can learn a lot by understanding how they are absent, because it's not so obvious, okay? And many familiar phenomena in string theory or quantum field theory can actually be re-derived just from require the absence of all these symmetries. So we'll see, but I don't know, like for example, if you start with the supergravity, I mean, if you work in string theory, maybe you know a bit about this, but if you work with the supergravity description of type 2 in 10 dimensions, like just the closed string sector, you can start playing the game of how many things can I say about the rest of the theory just from requiring the absence of global symmetries. And it's very cool that the existence of brains, also the Chern-Simons terms, and so on, and all these processes of brains, intersecting brains, and dissolving in brains, and so on, can be re-derived just from requiring that the theory doesn't have global symmetries. So it's actually more constraining than what we think. And also, other things that can be derived from what we see is that gauge groups are compact, or that the spectrum of charges is complete. Okay, so I will give you examples of this. And just so you know now, the completeness of a spectrum, it was another Swampland conjecture. I mean, that was written also, I mean, it's also quite old, that the spectrum of charges have to be complete. And now we are relating this to the absence of global symmetries, precisely making use of all this generalized notion of symmetries. Okay, so the goal here on the Swampland program is also try to unify these conjectures to try to identify what is the minimal set of statements that reproduces everything, to identify what is the quantum gravity underlying principles behind.
Sorry, so all the symmetries have to be gauge symmetries, and now you're saying that all the gauge symmetries have to come from compact gauge groups also.
Yeah, yeah, like exactly. And here I was thinking of continuous. Let me put continuous.
Right. Okay.
Okay. Otherwise, finite.
Because if you talk about these dualities,
yeah.
then I could see.
No, this is about continuous gauge groups. They have to be compact. Discrete, they don't have to. I mean, you can see that if you have a continuous gauge group that is non-compact, then you can have like a global symmetry in the sense that you have like a particle with charge 1 and a particle with charge square root of 2, and they can never decay one into the other. So you have like selection, like different sectors that are decoupled.
Thanks.
Okay, so for the rest of maybe the last 5 minutes I can take.
Okay, and then we should go to the discussion, Irena.
Okay, so I will try then to be less than 5 minutes, okay? So just, I want to give you, just to finish, what is the sharper definition for these global symmetries, okay? And tomorrow we will start with generalized notions of symmetries, okay? But at least for the zero form global symmetries we are talking about, let's try to make it sharper. So recently, the formal use to talk about global symmetries is in terms of topological operators. Okay, so this is something that is going to be useful for you regardless of the Swampland program, because there is a lot of activity here. So in order to describe, I mean, a global symmetry is going to be characterized by a unitary local operator, okay, that lives in d-1 dimensions, we'll see why, and is labeled by an element of the group, such that this operator is topological, okay, so it's a symmetry, so it has to commute. It's like saying that commutes with the Hamiltonian, right? So in quantum field theory, it has to commute with the stress energy tensor, so it has to be invariant under small diffeomorphism, which means that this operator has to be topological. Okay, this is the main point. And also needs to have something that is charged under it. Okay, otherwise there is no symmetry to talk about. So it must act non-trivially on some gauge invariant charge local operator. Okay, so that if I apply this unitary symmetry operator, this is not invariant. Okay, and this charge operator creates particles. Okay, creates a particle in your theory that is charged under the global symmetry. And the third condition, which can see actually can be relaxed, is that it satisfies a group law. Okay, but for the ordinary notion of symmetry, I mean, we require that they satisfy a group law. So in the example, I mean, with this I finished. The example we studied, right, was just some scalar field. The unitary operator that we had is just the exponentiation of the charge, of the global charge. So in this case, since we have a current, right, is the exponentiation of the integral of this current, which, if you remember, we said it was the integral of star d phi. And now you can see that this, right, is star d phi. So d phi is a one-fold current. So when you compute the Hodge dual, you get something that is a d-1 form. Okay, so this is the number of dimensions. Okay, this is dimensions. So this has to be integrated on a d-1 for manifold. Okay, so that's why these symmetry operators, okay, for zero form global symmetries like this one, live in d-1 form manifolds. And the charge operator is just a exponentiation of the axiom. Okay, so what happens now? We are saying, and with this I finish, we say that the symmetries have to be broken or gauged. So if the symmetry is broken, right, then this is no longer true. The operator is not going to be topological, it's not going to be conserved. Okay, and if it's gauged, what happens is that the second condition is not satisfied, because then I don't have gauge invariant charge operators, because this operator that I'm writing here is no longer gauge invariant when coupled to the gauge field, right? Because the transformation of the axiom has to be reabsorbed with a gauge transformation of the gauge field. So this charge operator is no longer gauge invariant. Okay, and this is the definition I was talking about. You just have to check what are the topological operators that you have in your theory. So that tells you what are the possible global symmetries. And then you have to see if there is any gauge invariant charge operator under it. If there is, then it's a global symmetry, and that should not be compatible with having a quantum gravity description at high energies. Okay, so let me finish here. Thank you for listening, and tomorrow we will continue with the generalized notion of symmetries and jump.
McGill. So you ready to go, Alex?
Yes, I think so. Everyone can hear me okay? Okay,
I can hear you
thank
fine.
you.
Yeah.
Great. So it's a great pleasure to be speaking today. You know, I wish I was there in person. I haven't been to the ICTP in almost 10 years. Great coffee, if I remember correctly. So I wish I could be there in person, but we'll have to make do. So I should begin really with an apology, because I see the names of many people who I know, you know, attending today. Unfortunately, if I know you, probably, you know, I'm going to bore you today, because what I'm really going to try and do, at least for this lecture today, is keep things really quite elementary. So my goal for this first lecture is to give a very general kind of schematic overview, really emphasizing some basic stuff, some background, so that we really can all be on the same page when I get into some of the more detailed aspects of these lectures starting tomorrow. So I'll begin by just describing a bit of a plan for what I'm going to do today. So I'm going to be presenting this sort of new view of holography and the AdS-CFT correspondence that's emerged over the last 2 to 3 years, I would say, although there were some precursors going back maybe more than a decade. But really, to begin, before I present this new view of holography, what I want to do is start by spending perhaps half of the first lecture today reminding everyone of the standard view of holography, you know, the one that you would learn if you picked up any one of a number of excellent lectures on the AdS-CFT correspondence. And then, after spending a little bit of time reviewing the standard picture of holography and AdS-CFT, I'll move on to talk about some recent indications, some hints that this might not be the whole story. In particular, I'll talk very schematically about the Euclidean path integral and how when we try and construct precisely theories of gravity based on path integrals, we discover things that are known as Euclidean wormholes. And these inevitably require us to change a little bit our point of view of holography. And in particular, they introduce this notion of ensemble averaging, which I'll be talking about in great detail as these lectures go on. And finally, and the main focus of my lectures this week, and something that I'll really only introduce today very schematically if I have time, I'll talk about the two main examples of theories of holography that incorporate this notion of ensemble average. So the first of these is, at this point, famous theory of gravity in 2 dimensions known as JT gravity, which can be formulated in terms of a matrix integral. So that is to say, as a matrix model. And then I'll be talking about a theory that was described more recently in a paper that I wrote with Edward Witten, as well as in another lovely paper by Afkhami Jetty, Tashdini, Hartman, and Cohn, where this describes a different theory of gravity known as U1 gravity, which is related to an average over a space of CFTs. And then I'll end, this isn't something I'll even get to today, but probably later on in these lectures, by talking about some speculations about what this means more generally for our understanding of quantum gravity, of general relativity, and where all of this stuff is going. Okay, so that's my plan really for these lectures. Today, what I'll really just be focusing on are these first 2 points, which I'll introduce rather schematically. But as the other lectures have mentioned, and before I get started, I want to encourage everyone to stop me, interrupt and ask questions if anything is unclear. Or on the other hand, if you feel like the things that I'm doing are too simple, too elementary, then feel free to interrupt me as well and encourage me to go faster or bug me about the details, because I love nothing more than getting distracted to talk about, other sorts of details. So that's all just to say, please feel entitled to interrupt me and ask questions at any point. Either just unmute yourself and ask a question, or you could go ahead and type something into the chat. Good. So let's begin by just reminding ourselves of what exactly we mean by holography. And in particular, holography is an equivalence, or at least the standard version of holography that you might read in a textbook is an equivalence between a theory of gravity in anti-de Sitter space and a conformal field theory living on the boundary of anti-de Sitter space. So before I get into any details about how we're going to modify this picture of holography to incorporate ensemble averaging, I'd just like to talk for a few minutes about where this comes from and why it's interesting. So to begin, and just to set some sort of common notation so that we all are on the same page, let me just think about the simplest setting for AdS CFT, which is an example that I have come back to many times in my work on the subject, which is 3-dimensional anti-de Sitter space. So what is anti-de Sitter space? Anti-de Sitter space is the maximally symmetric solution of general relativity with a negative cosmological constant. So typically, we would write the cosmological constant as 1 over L squared, where L is a parameter with dimensions of length known as the AdS radius. And then one way to describe anti-de Sitter space is by embedding it in one higher dimension. So for example, if you were to talk about AdS3, then you would embed it in a 4-dimensional space with coordinates that I have called here t, s, x, and y. This is a Lorentzian space, and I'm embedding it in a higher dimensional space-time with 2 Lorentzian directions, so that when you look at the induced metric in 3 dimensions, you'll get a Lorentzian signature space-time with 1 time-like direction. And if you were to try and write down a metric on this 3-dimensional anti-de Sitter space, then there are, of course, many different metrics that we can choose. I'll just introduce a couple of them that will be helpful to us as we move forward in our discussion of AdS CFT. So here I'm introducing a radial coordinate rho, a time coordinate t, and an angular coordinate phi, so that if you were to compute the induced metric in terms of these t, rho, and phi coordinates, that's a straightforward exercise, which you can almost read off from the embedding coordinates that I've written down here. Basically, I've written down these coordinates just so that we can all have a clear picture of anti-de Sitter space in our heads today as we move forward with these lectures. So you can see here that we have a time coordinate, an angular coordinate, and a radial coordinate. The picture that I want you to keep in your head is of AdS as a sort of solid cylinder. So here in this diagram that I'm drawing of AdS, t is a coordinate that runs vertically, that's the time coordinate. Phi is an angular coordinate that's periodic. You can see that it's periodic because the coefficient of d phi squared in the metric shrinks to 0. Okay, so that means that it has to be periodically identified. So near the origin, the metric looks like d rho squared plus rho squared d phi squared. That means that the metric is periodically identified phi with phi plus 2 pi. And then finally, you have a radial coordinate that fills in the solid cylinder. And in particular, at rho goes to infinity, we have a boundary. And you should think, although this boundary sits at infinite distance from points in the interior of AdS, I really want you to try and think of, so I've drawn a picture here where everything has been rescaled and I've pulled that boundary into finite distance. And this boundary is a cylinder, which in this picture is a time coordinate times a circle. So these coordinates that I've written down are the global coordinates of 3-dimensional anti-de Sitter space. For the purposes of comparing to other metrics that I'm going to be writing down later, I would just like to rewrite these coordinates a little bit to make them maybe a little more familiar to you. So in particular, instead of using rho as a radial coordinate, instead, I want to use a radial coordinate that is the coefficient of d phi squared in the metric. Okay. So if I define a new coordinate r, which is going to be L times sinh rho, then it's easy enough to go ahead and write down what the metric looks like in those coordinates. So not much happens to the metric. This is just a straightforward exercise. And these are the conventional coordinates known as the global coordinates of AdS. They cover all of the Lorentzian AdS geometry. Okay, good. Now, we began today by saying that holography is a relationship between a theory of gravity in AdS and a conformal field theory. But there's a very important point that I want to make, which is that when we study gravity in AdS, we are not just studying anti-de Sitter space. Instead, what we are studying is not just AdS, but we are studying all spacetimes that look like anti-de Sitter space out at infinity. That is to say, that look like AdS asymptotically. So asymptotic infinity. So not just AdS. So we're not just studying AdS, or even just perturbation theory describing small fluctuations around AdS. And so what that means is that when we define theories of gravity in AdS, we need to be very careful about describing the boundary conditions of our theory of gravity under consideration. So gravity in AdS is not just, a theory of metrics related by diffeomorphisms, but it's also a theory that includes a very careful and precise definition of boundary conditions. Okay. And in fact, it's those boundary conditions that really will lead us to think about holography and the AdS CFD correspondence. Okay. So for example, there's another an easy way to describe this is to actually use a different coordinate system that will also be useful to us as we move forward. So these are not going to be a global coordinate system, but what are known as planar or Poincare coordinates. So this is a different set of coordinates on AdS. So where I'm going to have a radial coordinate r, and now I'm going to introduce coordinate systems, a coordinate system that is adapted to the planar symmetries of AdS. So here we have a metric on a two-dimensional plane that I'm describing using a complex coordinate z, along with a radial coordinate. Okay. And these are supposed to be lectures. So because these are lectures, I feel entitled to assign homework. So your first homework exercise is going to be to find the coordinate transformation that relates these global coordinates to these planar coordinates that I have written down here. And so now, given these planar coordinates, it's easy for me to define exactly what I mean by geometries that look like AdS at infinity. So what I mean is that I want to consider the class of metrics that approach the metric that I wrote down above in planar coordinates, plus terms that are subleading. So what do I mean by subleading? Well, in terms of these planar coordinates on AdS that I have written down, the boundary of AdS is often r goes to infinity. And so all I want to do here is I want to consider the class of geometries that look like this boundary metric, this AdS metric, plus terms that are subleading as r goes to infinity. Okay. Good. So the reason why I'm being very persnickety about defining my theory of gravity in terms of some set of boundary conditions is that once I've defined these boundary conditions, I can talk about the symmetries of the theory. And in particular, the symmetries of AdS. And I should be a little bit more specific and say the symmetries of gravity in AdS are the diffeomorphisms, that is to say, changes of coordinates that preserve this form of the metric. And so given this form of the metric, it's a straightforward exercise. Okay, again, I'm using the word exercise because I'm too lazy to work it out for you exactly. So instead, I'll assign it to you as a homework problem. It's a straightforward exercise to find the class of diffeomorphisms, that is to say, the class of changes of coordinates that preserve this asymptotic form of the metric. So in particular, what are they? Well, Z here is a complex coordinate. And so it turns out that for any holomorphic function epsilon and anti-holomorphic function epsilon bar, you can find a diffeomorphism of this three-dimensional geometry that just takes Z to Z plus epsilon and Z bar to Z bar plus epsilon that preserves these boundary conditions. Okay? With a little bit of a wrinkle, which is that if you work it out, there are corrections that you need to include in order to get everything to work out so that you end up preserving these boundary conditions. And here the radial coordinate will have to change as well. So the reason why I've gone through the trouble of writing all of this definition of exactly what I mean by gravity in AdS and exactly what I mean by the symmetries of gravity in AdS very carefully is the following. Okay? So usually when we think about a theory of gravity, what we do is we talk about the diffeomorphisms of our theory of gravity as gauge symmetries. Okay? But that's not actually the right way of thinking about gravity in AdS. When we think about gravity in AdS as a theory defined with a set of boundary conditions. Okay? In particular, it's only those diffeomorphisms where this function epsilon equals to 0 that we regard as pure gauge. And what do I mean by that? Well, what I mean is that metrics related by these diffeomorphisms are regarded as being identical. So usually when you think about a theory of gravity, like when you learn general relativity, you learn that general relativity is a theory of geometry, not a theory of metrics. Right? And what do we mean by that? What we mean by that is that any two metrics that are related by a diffeomorphism, a change of coordinates, describe the same geometry. So for example, if you were trying to construct a path integral, they would give you one contribution to a path integral, not two different contributions to a path integral. Or if you were talking about classical solutions of general relativity, any two classical solutions that are related by a change of coordinates, they're not different classical solutions. They just describe one classical solution. And the rule of the game when we're studying gravity in AdS is that the diffeomorphisms that are regarded as gauge symmetries in this sense are only those where the function epsilon is equal to 0. And diffeomorphisms with epsilon not equal to 0 are not pure gauge. Instead, they generate symmetries of the theory. So in particular, what do we mean by that? What we mean is that two metrics in anti-de Sitter space, here, let me scroll up so you can see the metric up above. Two metrics in anti-de Sitter space that are related by a change of coordinates are not regarded as being identical if that function epsilon that I have written here is non-zero. So what does that mean? That means that these diffeomorphisms of general relativity and AdS are actual symmetries of the theory in the sense that they take you from one state to another. Okay, right? What is a symmetry? A symmetry is something that takes you from one solution of the equations of motion, say, to another solution of the equations of motion, different solutions of the equations of motion. Or it's something that in the quantum mechanical picture would be a unitary operator acting on the Hilbert space that would take you from one state of the theory to a different state of the theory. The important ingredient that I'm trying to emphasize is that when we talk about gravity and AdS, the diffeomorphisms that act non-trivially out at infinity in the sense that epsilon is not equal to 0 are actual symmetries of the theory.
Excuse me?
Not gauge symmetries. Yes, please.
You mean pure gauge is epsilon equals to 0? Does that mean you only have the subleading corrections, or?
That's correct. So a diffeomorphism that is purely subleading in the sense that it only lives in those ... dots that I wrote down above is regarded as a gauge symmetry.
Okay, thank you.
We have other things where epsilon is not equal to 0. These are not symmetry. These are not gauge symmetries. These are actual physical global symmetries, if you like, of the theory. And what are they? In order to understand what they are, let's ask how they act on the boundary of the theory. How do they act on the boundary of AdS? Well, they take z to epsilon plus z plus epsilon of z, where epsilon is some holomorphic function of z. So out at infinity, these symmetries of the theory, not gauge symmetries, real symmetries of the theory, take z to some holomorphic function of z and z bar to some anti-holomorphic function of z. Okay. How do these act on the boundary? Well, out at infinity, the boundary looked like some radial factor times dz bar. And if you were to write this in terms of the w coordinate that I wrote down over here on the left side of this slide, well, you'll see that this change of coordinates that is an actual symmetry of the theory, not a gauge symmetry, an actual symmetry of the theory, ends up just multiplying our metric by an overall factor. Now, we have a name for a transformation of a metric that multiplies the metric by an overall factor. It's a conformal transformation. So this is a conformal transformation that takes the metric to some function times the metric. So in particular, coordinate transformations or transformations of the metric that just multiply the metric by an overall function preserve angles, but not lengths. That's why these are known as conformal transformations. Okay? So just to summarize, what we have seen is that diffeomorphisms that act non-trivially on the boundary of anti-de Sitter space are two things. The first is that they're not gauge symmetries, right? Because of our definition of what we mean by gravity and AdS. And the second is that they are conformal transformations of the boundary. And these are the two ingredients that really underlie the AdS-CFT correspondence, which is the idea that a theory of gravity in anti-de Sitter space is a conformal field theory. So this is the basic kinematic statement of AdS CFT. Now, what do we mean exactly by this statement? Well, when I say equals here, I really mean equals, okay? And so there are really a couple of different ways of thinking about this duality. One way of thinking about this is to think about it in Lorentzian signature. So in Lorentzian signature, you define a quantum theory by a Hamiltonian and a Hilbert space, okay? And so when I say that these theories are equal, I mean equal in the sense, sorry, my pen is acting up, in the sense that the Hilbert space of quantum gravity in AdS is supposed to be the Hilbert space of a CFT. And that the Hamiltonian that describes time evolution of our theory of gravity in AdS is the same as the Hamiltonian of the CFT, okay? So when I say equal, the standard view of the AdS CFT correspondence is that these are really two quantum theories that are equal, same Hamiltonian and same Hilbert space. Or if we were to talk about the theories in Euclidean signature, what I mean is that they have Euclidean path integrals that are equal. So here on the left-hand side of this equation, I am thinking about the gravitational path integral of a theory of gravity in AdS regarded as a function of boundary data. And that is supposed to be equal to some CFT path integral. Okay. So this is the traditional point of view of gravity in anti-de Sitter space. And if this fixed perspective is true, then this is great, okay? Because if this is true, it answers some of our most confusing questions about quantum gravity. And in particular, it answers what I think of as the big question of quantum gravity. So in particular, I think that the big question of quantum gravity is quantum gravity a normal theory? That is to say, a normal quantum theory with a Hamiltonian and a Hilbert space, and with time evolution described by, a standard unitary evolution with this Hamiltonian on the Hilbert space. Or to really state that a little bit more differently, it also answers the big question, is black hole entropy counting the number of states in some standard quantum system in the usual way, where an entropy would be the log of the number of microstates. So why does this AdS CFT correspondence answer these questions? Well, in particular, if you can identify the Hilbert space and Hamiltonian of AdS gravity with that of a CFT, then it says yes, quantum gravity is a normal quantum theory. But it also answers the second question, because gravity in AdS is a rich theory of gravity that includes black holes. And if those black holes are living in some nice quantum theory, then black hole entropy is just doing the usual thing that we expect in any sort of theory of statistical mechanics, where an entropy is counting the logarithm of some number of microstates. And indeed, if you read any standard review of AdS CFT, they'll present a huge amount of evidence that this works and that the AdS-CFT correspondence is correct for certain, what I will call fancy theories of gravity. So the standard example, which is probably the defining example of a fancy theory of gravity, would be something like type 2B string theory on AdS5 cross S5, which is via AdS-CFT supposed to be dual to a conformal field theory that is supersymmetric, n equals 4 SUN Yang-Mills theory. Okay. So, of course, there's, probably 10,000 papers, probably more than 10,000 papers written, collecting evidence and understanding this duality, unpacking it in various ways. Every calculation that we have done so far seems to indicate that it is correct. But the problem is that since this is a strong weak coupling duality, really, as any duality worth its name is, it is difficult to study both sides of this at the same time. So in particular, if you were to try and study the classical limit of gravity on the left-hand side, then that corresponds to strongly coupled Yang-Mills theory on the right-hand side. So in particular, supergravity on AdS5 cross S5 corresponds to the large N limit of Yang-Mills theory, but it's strong at Tooth coupling rather than at weak Tooth coupling. And even worse, if you wanted to try and understand genuine quantum effects in our theory of gravity, then that would mean not just studying SUN Yang-Mills theory at strong at Tooth coupling, but also understanding it at finite N, okay, which is a very difficult thing to do. It's a very complicated problem in strongly coupled gauge theory. And so, in fact, pretty much nearly every check of the AdS-CFT correspondence involves working perturbatively on one side or the other. And what we would really like to do is to understand this more precisely in a setting where both sides of this correspondence can be studied explicitly. In particular, I think most people would agree that we don't have a non-perturbative definition of what we mean by type 2B string theory on AdS5 cross S5. We have a lot of incredible evidence that such a theory exists, that it can be studied in various different limits using various perturbation theory techniques, but we don't really have a rigorous non-perturbative definition of the left-hand side of this correspondence, independent of the right-hand side. And in fact, I think the modern point of view is probably that we should define type 2B string theory on AdS5 cross AdS5 via this duality and say that there's a sense in which it is equivalent almost by definition to n equals 4 SUN super Yang-Mills. But we would really like to try and understand, whether there are theories of gravity where we can compute both the left-hand and the right-hand side of this correspondence exactly and independently. For example, what we'd like a gravitational theory where we can compute something like a path integral over a space of metrics. Okay. So we don't have a definition of string theory, which would allow us to compute this, independent of some AdS-CFT correspondence. So instead, what I'm going to do is just try and find some sort of simpler thing, okay, where we can hope to compute this thing exactly. But even before we do so, what I want to emphasize is that in many cases, there is a strong tension between the existence of such a path integral and the AdS-CFT correspondence as I have defined it above. Okay. So what is that tension? Okay. So in order to understand that tension, let's just begin by asking, if we can't compute this path integral over a space of metrics exactly, how would we go about approximating it? Well, the way that we would approximate this path integral is the way that we always, approximate path integrals, which is through a saddle point approximation. So for example, I left out my h bar here. I should really put a 1 over h bar here. And then in the h bar going to 0 limit, you would approximate this path integral as a sum over classical saddle points. So these are saddle points that I have called G0, which are going to be solutions to the equations of motion. Okay. And here I've just written down the classical contribution coming from each saddle point. If we're thinking in Euclidean signature, we would call these saddle points instantons. And so I'm thinking about the classical instanton contribution to a gravitational path integral. Okay. Now, in order to understand what this would tell us about AdS-CFT, AdS-CFT tells us that this gravitational path integral, so let me try and define it a little bit more precisely. So this is going to be something like a sum over a space of metrics weighted by some kind of Euclidean action, because I'm now imagining a Euclidean path integral. And I have a boundary that I'm calling sigma here. And I want to sum over all geometries whose boundary is equal to sigma. So you should think about this as a sum over manifolds M whose boundary is given by some surface sigma. And the claim is that this should be equal to some CFT partition function on sigma. Now, what CFT partition function it is depends on, well, what CFT sits on the right-hand side of the AdS-CFT duality, but it might be something like, for example, a theory of a bunch of bosons. Okay, that would be the simplest possible example. And then what do I mean by this CFT partition function? Well, I literally mean the path integral over the CFT degrees of freedom. And here, the boundary is literally just the surface that these fields live on. So for example, if we're thinking of a bunch of bosons, then these bosons would be maps from that surface into whatever the target space of my CFT is. So that's just the sort of example of something that you might expect to live on the right-hand side of the AdS-CFT correspondence. Okay, it's an equivalence between two functions, one of which is supposed to be a gravitational path integral, a sum over all metrics with some specified boundary. And the other is supposed to be a CFT partition function, where you compute the partition function of a bunch of degrees of freedom that live on that surface out at the boundary. Okay. But a basic fact.
Alex?
Yes.
Can I ask you a question?
Please.
Regarding the semi-classical approximation, should we be worried about the action being bounded below?
You should be worried about all kinds of things. Okay. In order for me to make this story precise, I'm going to need to talk exactly about how I do this Euclidean path integral. So, for example, when I talk about an action of Euclidean, of some geometry, then I need to regularize it in an appropriate way. So when we talk about gravitational theories in AdS, we have a machinery holographic where we introduce boundary counter terms that allow us to regulate this in the appropriate way. So when I talk about a classical action, I really need to talk about a regulated classical action in that sense. There are also some dots in that expression up here that I very carefully left out. So for example, and I think this might be one of the things that you're alluding to, which is that when we talk about Euclidean path integrals of gravitational theories in AdS, it actually turns out that one of the degrees of freedom appearing in this path integral appears to be a Gaussian with the wrong sign in the effective action. So you actually would appear to get something unbounded below when you look at linearized perturbations around Euclidean saddle points. In the study of perturbative gravity, there are ways of dealing with this that involve very careful contour manipulations that allow us to turn this from a wrong sign Gaussian to a right sign Gaussian. And so when we compute the subleading loop corrections of a theory of gravity in AdS, so here in those dots, that would be like a one loop effective action or two loop contributions and so forth. These are all things that we're going to need to try and deal with precisely. Okay, I'm trying to be a little schematic right now, so I'm kind of brushing that under the rug, but those are all things that we're going to need to try and deal with precisely. But in that case, with the wrong sign, right sign Gaussian nonsense, that's a standard field theory thing. But all of this can be summarized by saying that I agree with the spirit of your question, which is the following, which is that I am trying to study a theory of gravity and Lorentzian signature. But at the end of the day, only a dummy cares about, sorry, let me restate that sentence carefully. What I'm studying here is a path integral in Euclidean signature, right? I'm doing a Euclidean gravity path integral. But really, at the end of the day, we don't, only a dummy would care about Euclidean signature. We care about Lorentzian signature physics, Hamiltonians and Hilbert spaces. And to go from Lorentzian to Euclidean signature, what you need to do is understand very carefully what kind of contour deformation you're doing to go from Lorentzian to Euclidean signature. And so when I wrote down this equation up above, I was really making a subtle assumption, which is that there is a contour, when I go from a Lorentzian to Euclidean signature, there is a contour through the space of metrics, which is, the stationary phase contour, and that the saddle points that appear as contributions to this integral in the stationary phase approximation are just the usual solutions to the Euclidean equations of motion. Now, nobody really understands exactly how to define precisely the contour that would define a Euclidean gravity path integral. And all we really know how to do is follow our nose, so to speak, and try and see what makes sense. And so what I'm going to do today is kind of write down some things, some contributions that seem to make sense. But what you're saying is absolutely the right question. And I think one, really what we should try and do is define a theory of gravity completely precisely by defining exactly what contour of integration through the space of metrics we are studying. And then that would allow us to determine exactly which solutions to the equations of motion would need to appear in that top equation on the slide. But for now, let me just, I don't have a ton of time left. So let me now just try and get to the punchline of what I was trying to get to today.
Thanks.
Okay. So a basic fact about CFT partition functions is that if our surface that our CFT lives on is the disconnected union of two other surfaces, then the CFT partition function factorizes. So it'll just be the product of the partition function on those two surfaces. Okay. But in many gravitational theories, this does not appear to be true. In particular, if I try and study these CFT partition functions and compute them by doing a gravity path integral, what we find is that they don't factorize. Okay. So let me just present a sort of simplified version of the argument that these gravity partition functions don't factorize. Okay. So let's just talk about a silly, okay, two-dimensional example. So this would be AdS2 CFT1. So here, let's imagine that our boundary is a circle. And it's going to be a circle of some length beta. Okay. I've called it beta because a circle of length beta is what you would study if you wanted to compute the finite temperature partition function. So here, I'm imagining that we have a CFT in 1 dimension. This is just a sort of dumb toy model. The Hamiltonian is the thing that generates time translations around the circle. And the partition function of the theory on the circle is trace of e to the minus beta h. That's the usual statement in thermal field theory. E to the minus beta h is the Euclidean time evolution operator that moves you a distance beta in Euclidean time. Okay? So how would you go about computing this via some sort of AdS CFT correspondence? Well, in the bulk, what you would need is a geometry M whose boundary is a circle. That is to say, we would need a disk. And indeed, we're imagining a theory of gravity in AdS. So you're looking for AdS metrics on the disk, or in Euclidean signature, we would call them hyperbolic metrics on the disk. And there is a simple hyperbolic metric on the disk. It's just the two-dimensional version of a metric that I wrote down for you above. Here, I'm calling the angular coordinate Euclidean time because I'm thinking about this in terms of the calculation of a finite temperature partition function. And this here is the metric on what we would call the Poincare disk, otherwise known as Euclidean AdS2 or two-dimensional hyperbolic space. Okay, all of this is fine. It means that if you were to compute the CFT partition function at finite temperature, it should be something like the gravitational action of the disk. Good. Okay, so now it's the end of the lecture and I can stop and we can all go home declaring victory. Okay. Except I'm going to steal a few more minutes of your time and show you that life gets more complicated once we consider more interesting observables. So what about our boundary being the union of two of these circles? Okay. So what sort of geometries could live in the gravitational path integral that computes the CFT partition function on a pair of circles? Well, one option is the disk union the disk. Okay. There's a picture. Our boundaries are disconnected and our bulks are disconnected. But if you think about it, there's another option, which is the cylinder. So in particular, there's another locally AdS metric, that is to say hyperbolic metric, whose boundary is 2 circles. And I chose to work in 2 dimensions because it's very easy to write down the metric. There it is. This now has 2 boundaries. One at R goes to minus infinity, and one at R goes to plus infinity. It's locally AdS. So if AdS is a solution, then this cylinder is going to be a solution as well. And this is what we would call a Euclidean wormhole. It is a Euclidean wormhole, and that is a Euclidean solution with 2 boundaries, 2 disconnected boundaries. Okay.
One question.
So what does this mean? Yes.
This, I mean, here in the first example, we could also have, for example, a torus without a circle, and in that case, we would also have like a 2-dimensional manifold whose boundary is a circle. So why are not we taking it into account?
In the full, because I am being simple here, and I am just writing down 2 representative solutions. In particular, I wrote down the cylinder because it's the simplest one that's going to lead to a puzzle. But of course, there are going to be other options as well. Okay. So for example, you know, there are things that look like this.
Yeah.
And in a full theory of gravity, I would need to sum over all of them. And indeed, that's exactly what happens in JT gravity. Okay. Now, in a theory of gravity, you would weight these guys by their Euclidean action. In the present case, the Euclidean action is just, you know, includes a factor of the Euler character. So there's going to be a genus expansion in our theory of gravity. So all that higher genus stuff is going to be suppressed.
Okay.
But it will be there. Good. Great question, actually. Great
question. Thanks.
Good. Thank you. Okay. But this is a problem. So it appears that the gravitational calculation of this thing does not factorize. So here I've given you a super dumb example in a 2-dimensional theory of gravity. But these Euclidean wormholes, it turns out, are ubiquitous in all sorts of theories of gravity. This was originally pointed out in the AdS CFT context in a lovely paper by Maldacena and Maus that's probably, you know, written 15 years ago at this point. And I think of this Maldacena-Maus paper as the starting point for this whole story of gravity and ensemble averaging. Okay. So what I've done here is present the puzzle. And what I now want to do in the last -5 minutes that I have remaining in my lecture today is present one potential resolution of this puzzle. Okay. So what is the possible resolution of this puzzle? So the possible resolution is that we should interpret our gravitational partition function, by which I mean an integral over a space of metrics with a specified boundary, not as a CFT partition function, but as a sum of many CFT partition functions. So here, what I'm going to do is I'm going to label my CFTs by a capital letter C, and I'm going to imagine that my gravitational partition function is going to be an average of many CFT partition functions, averaged with some probability density over the space of conformal field theories. So this is a kind of radical reimagining of the AdS CFT correspondence, right? AdS CFT is supposed to be a relationship between a theory of gravity and a CFT. Okay. You might think in that statement, in that sentence, the words theory of gravity and conformal field theory might be the most confusing words in that sentence. But instead, the most confusing word in that sentence is A. Because in this interpretation, AdS-CFT is not a relationship between a theory of gravity and a CFT, but a relationship between a theory of gravity and an ensemble of CFTs, described by some sort of probability distribution. So let's now return to the calculation I did a moment ago and understand how we would interpret this cylinder amplitude in terms of this probability distribution. Okay. So in particular, let me think now about ensemble averaging. So if I have any CFT observable, let me denote the average of that quantity using angular brackets. So for example, the gravitational path integral I wrote down above is going to be the average in the sense of a CFT path integral. Then let me repeat the calculation that I did above. So the gravitational path integral on a circle is going to be basically, so that's the thing that at leading order was the gravitational action of the disk. This I interpret as the average thermal partition function of my CFT. Okay. But now, what is the interpretation of the gravitational partition function on the union of two circles? Well, one of the bulk saddle points was two disconnected disks, and another was the gravitational path integral on the cylinder, at leading order the action of the cylinder. And this is the thing that I interpret as the expectation value of the partition function squared. Okay. But what is this term here? This term is just the square of the expectation value. Right? That's just this first line up here. Okay. So what does that mean? That means that this cylinder amplitude of my gravitational theory, using very sophisticated mathematics, where I move that trace of e to the minus beta h expectation value squared onto the other side of this equation, is the variance of the partition function. So the lesson that we draw is that the existence of Euclidean wormholes implies, or at the very least, strongly indicates that AdS-CFT is describing an ensemble of CFTs with a variance that is not equal to 0. And for example, the classical action of the cylinder solution of our gravitational theory is the variance. And if it's non-zero, then our variance is non-zero, and we have some sort of probability distribution. So let me just end. Well, first I'll apologize for going over time. I think I was only supposed to take 50 minutes. So I apologize for that. And let me just end with an advertisement for the next few few lectures. So far, I've been extraordinarily schematic. What I'm going to be trying to doing over the next 3 lectures is to describe to you 2 different models. The first is JT gravity. The other is a theory of gravity that I'll refer to as U1 gravity, where this ensemble averaging can be made precise. And along the way, what I'll try and do is sort of, be honest to you about the things that we do and the things that we do not understand in this emerging picture of holography and averaging. But why don't I stop there and take some questions?
Let's thank Alex for this opening lecture.